In this work, we present our work titled Towards Edge Holography via Implicit Neural Representation and Compression. We propose a compact implicit neural representation for phase-only holograms, together with a compression framework that enables efficient hologram decoding on edge devices. Holographic near-eye displays have been widely studied for AR and VR, because they provide a physically meaningful way to reconstruct three-dimensional optical wavefronts. Compared with conventional display approaches, holography has the potential to offer more natural depth cues and a more compact optical form factor. For this reason, holographic displays have attracted significant interest as a promising direction for future near-eye display systems. In computer-generated holography, a coherent laser illuminates to a spatial light modulator, which modulates the optical wavefront from the phase-only hologram pattern. After propagation through the optical system, the hologram reconstructs the target scene. This allows us to display depth-varying three-dimensional content optically, rather than simply showing a 2D image. This shows that holography is a promising approach for true 3D display. However, generating holograms efficiently is still challenging. A widely used approach is to optimize the phase pattern directly with per-pixel iterative optimization, often called an SGD-based method. Because holograms require a fine pixel pitch, they usually involve a very large number of pixels, which makes both optimization and storage expensive. Compression is therefore essential for practical deployment. At the same time, optimized phase patterns are highly irregular and almost random, making them difficult to compress explicitly. Even slight phase distortion can easily ruin fine reconstruction details. For these reasons, direct per-pixel optimization and explicit hologram compression are not well suited for practical systems. Instead, we replace per-pixel optimization and image codec-based compression with an efficient global implicit representation, and we compress the parameters instead. This allows the phase holograms to preserve their fine details with compact representation. Our core idea is to represent the hologram using an implicit neural representation. Instead of optimizing and storing every hologram pixel directly, we feed spatial coordinates into a neural network, and the network outputs the phase-only hologram. We then propagate the generated hologram to the image plane and compare the reconstructed image with the target image at the desired depth planes. By optimizing, the network learns a compact neural representation of the phase-only hologram. To improve optical quality, we do not rely only on an ideal wave propagation model. Instead, we use a camera-calibrated wave propagation model during optimization. This allows the training process to better reflect the real hardware behavior and reduces the gap between simulation and optical reconstruction. As a result, the optimized holograms are more suitable for real display systems. Next, to make the INR compressible, we apply quantization-aware training. During training, the network weights are quantized with learned step-size quantization so that the model adapts to the constrained representation. After training, the quantized model parameters are entropy-coded into a compact bit stream. So, instead of compressing the explicit hologram itself, we compress the weight parameters that generate the hologram. And this framework shows a better compression results compared to. At the edge side, the procedure is simple. The edge device receives the compressed bit stream, performs entropy decoding, restores the model parameters, and runs a single forward pass through the INR to generate the phase hologram. Importantly, the edge device does not need iterative hologram optimization. This makes the decoding process efficient, and in our system, it reaches around 250 frames per second. Next, we show the experimental results captured using our unfiltered holography prototype. Here, we show two-dimensional optical captures. Our method, shown in the top row, provides higher contrast while using efficient compressed data. These results indicate that our approach can maintain strong optical reconstruction quality even under a compact neural representation. Here, we show the compressed two-dimensional holograms. Our method achieves higher compression ratios compared to conventional image codecs while maintaining competitive reconstruction fidelity. Our method shows a practical hologram transmission pipeline and high storage efficiency. These results show that compressing the neural representation is an effective alternative to compressing explicit phase patterns directly. Now, we move to three-dimensional hologram results. In this example, we zoom into a far plane region and change the focus. The top rows correspond to our method. We can see that our approach preserves the target depth more clearly, while still benefiting from efficient compression. This shows that the proposed representation also supports 3D holographic reconstruction. Here, we show the same scene, but now we focus on a near-plane region. Again, the results demonstrate that our method preserves the intended depth structure while maintaining good reconstruction quality. Together with the previous slide, these examples show that the proposed method works consistently across different depth planes in three-dimensional holographic scenes. Another important point is that our prototype is designed without a 4F filtering system. So you can see that we directly observe the holographic image from the SLM side in an unfiltered configuration. This is meaningful because eliminating bulky filtering optics helps move holographic displays toward a more compact and practical form factor. Based on this direction, our work supports the broader goal of compact holographic near-eye displays. By combining implicit neural representation, compressible model parameters, and efficient edge-side decoding, unfiltered holography, we move toward a more practical holographic pipeline for resource-constrained devices. To summarize, our work makes two key transitions. For hologram generation, we move from per pixel optimization to implicit representation. For compression, we move from explicit phase coding to compact parameter coding. Together, these shifts bring us closer to fast and practical edge holography. Thank you very much for listening.